You know, my lab statistics, like where we're at in comparison to like. The questions,
How do you mean? So,
I think. Like, we should be able to answer through
oh, I see what you mean.
all the way through 13.2, right?
That's right, yeah.
And maybe the first couple on 13.3.
You could probably start it, but there's certain things we haven't done. We haven't done this whole thing yet in there. So we're only up through 13.2. Oh, looks like it's time to start. Welcome back, folks. Any other questions at the moment to start us out? Okay, well, I appreciate you all making it in today. It's definitely, I was saying earlier, we can kind of really feel the hour now that we're back in standard time with daylight savings times ending. But for the announcements, probably the biggest one is our third exam is going to be in 2 weeks from today. So that's going to be down here on the Canvas website. It'll be right before we go on our week holiday for Thanksgiving break, so that'll be kind of nice. Exam 3 won't be something looming on the back of your mind while you're on holiday. So we'll get exam 3 resolved here on Monday. And that means on Friday of this week, I'm going to put down what the exam 3 coverage is, the sample problems, just like we did on the prior exams. But it's looking at where we're at so far. It's going to likely involve, let's see, chapter 7 is where we left off. So there'll be a chapter 7 problem, a chapter 10 problem, and a chapter 13 problem, probably 2 of them. One of them is just going to be checking conditions, 13.2. I feel like that's a pretty big problem all on its own, saying what the statistic is, calculating maybe a standard error, but checking conditions. And then the last question is going to be just doing the full confidence interval problem, but not asking you to do the condition checking on the same time. So that's going to be really just split into 2 different problems. So that means quiz 7, quiz 8, and quiz 9 is going to be a pretty good coverage of what you're going to expect to see on that exam. And let me click on that. There we go. So that's where we're at so far, folks. We're just about to finish off chapter 13, but there's definitely a lot of good work to do here. This is where the whole procedure culminates, the confidence interval for a proportion. So we'll take our time with this one and potentially start chapter 14 if we're on Thursday, I'd say. But it's kind of another thing that's neat is this is the whole formula right here. We know what p hat is, we know what y bar is. We have to say what z star is, but that's just connecting through with the normal distribution, the normal curve. We've calculated the standard error p hat. We haven't calculated that standard error, but it's just a slightly different formula. And so if you can do it once, a confidence interval for a proportion, chapter 14 is just doing a whole different one for now quantitative data, handling one mean. So there's lots of parallelism here. All the logic that we get through in section 13.3 kind of carries over to the next chapter. But any questions at the moment, folks, before we get started? Okay, well, there's a whole bunch of text here, kind of like a wall of text. These are optional reading links. They take you to Wikipedia, one for Ronald Fisher, one for William Seeley Gossett. We'll talk a little bit more about them when we talk about the T distribution, the student's T distribution in chapter 14. So here's where we are so far. We just finished off the 13.2 section. It's now 13.3. Starts off with like a lot of sections and statistics, a huge wall of text. But think of what all this is just putting everything together. Chapter 13 had a lot of moving parts. We defined the statistic, the sample proportion of successes. So this terminology is just reminding us that that's the statistic, and it's estimating the parameter below. So this whole block right here is really just a carryover from section 13.1. Then in that same section, we introduced the central limit theorem. And this is the new stuff in section 13.2, the assumptions and conditions and computing the standard error. So this is really just a one-stop shop for all the concepts, formulas, and ideas thrown into one location. Any questions at the moment with any of those formulas or ideas so far? Okay, so the big idea is the central limit theorem. And now when you put it all together, the fact that p hat is estimating the parameter p, but it involves a margin of error that we estimate using the standard error and the normal distribution, you get this entire procedure right here. So this is finally the new stuff. The large sample confidence interval, large sample because sometimes sample sizes have to be pretty large for this to qualify as mean conditions. It's a confidence interval for a proportion p, a population proportion p of successes. Starts off by saying gather a simple random sample of size n from a population with unknown population proportion of successes p. Then there's two major conditions that we're going to check when we're in this section. We're not going to check every single thing. The independence assumption is not here. And we're not going to worry too much if our sample's too large relative to the population size. We carefully check that condition in the last section. But the two major things that we can double check are, did it mention anything about randomization? And is our sample size itself large enough to meet the success failure condition? So these are going to be the two elements that we focus mostly on in this section. So if those conditions are met, here's the whole formula. The population proportion p is estimated by taking the statistic p hat, add or subtract z star, a new symbol, times the standard error of p. Formula for standard error is over on the right. So if we can figure out what is z star, we have the entire confidence interval procedure down. Really, we've been kind of getting estimates of z star in the prior section just to see how all this comes together. We'll call this z the critical value z star. And down below just gives us a table lookup. If we're doing, say, a 90% confidence interval, z star is 1.645. We need to discuss where these numbers even come from in the very first place. For a 95% confidence interval, it's 1.96. And notice as confidence gets bigger and bigger, the critical number, z star, gets bigger and bigger as well. So just to get a good idea of what is z star really, let's calculate a weird one. The critical value z star that corresponds to 93.5% confidence. Let me change up this color coding a little bit so we can focus on the confidence versus the critical number. Well, there's one other document that I forgot to load up. I wish I did. Let's take a quick mental break while I grab this. Really, we're going back to section 5.3 again. This was the section we looked at not to do the normal model computation, but to think about it conceptually. What is the normal model? How do you draw it? Where is the areas in the normal model? And the big observation was approximately 95% of observations are within 2 standard deviations of the mean. That's kind of what this number is saying. It's a 95%, just like the middle rule right here for 95%. But the 2 standard deviations, which was an approximation, is more accurately 1.96. So this is where all the ideas connect, giving us the critical number z star and building out our entire interval. So let's calculate a couple of those just to see how they go. First, we put down a normal distribution. Let me try again with that curve. And one thing that's kind of weird about this already is you can put down any normal distribution you want whatsoever, because these 3 rules hold for any mean whatsoever and any standard deviation whatsoever. So if it doesn't matter what the mean and standard deviations are, the best picture that we can put down, or the easiest one to think about, is N01, the standard normal distribution. This means we're picking the mean to be 0 and the standard deviation sigma to be 1, like we were in section 6 or 5.4. Those are the values we'd throw into the calculator. That means the center here is 0. And if we're doing a 93.5% confidence interval, it means we're capturing the central 93.5% of the area. Our number is going to be kind of close to 2, but just a little bit off. So here's what we would draw next for our sketch. Go from about here to about here. We now have the central area, 0.935. Make that a little bit bigger. So this is now 0.935 for the central area under this curve. Keep in mind, don't forget that whatever this number is has to be written as a decimal number. And some people's calculators could handle this number just as it is. What we're going to use is the good old function inverse norm. And the reason is because we're trying to come up with a number here, which we're going to call z star. Those are the numbers we see in the table. We're computing a new one for that level of confidence. Over here is negative z star. And now this just turns into a calculator computation. So here's the challenge with our calculators, though, is everyone has a slightly different TID4 in class. So some people might be able to set center area to 0.935. If that's your calculator, you're good to go. If your calculator looks a little bit more like mine, the only area it's going to accept is the left tails area. So that's the number we're going to put in. So the area that goes here is found by this formula. It's 1 minus whatever the confidence level C comes out as. Forgot to fix that pen. Divide by 2. The reason it's divide by 2 is we have the confidence inside here. So we have also in this right tail area is 1 minus confidence, divide by 2 as well. So these are the two formulas. If you add all three of these things together, if you take the center confidence, then 1 minus C split over 2 tails, you get just the total area, which would be exactly 100%. So what we're calculating is 1 minus 0.935. Actually, let me try to fit that in better. 1 minus 0.935 divide by 2. And this is the actual area my calculator that you see up here would accept. So back over here, go 1 minus 0.935 divide by 2, and we get that number 0.0325. And let me make this arrow be a little bit more sensible. So that goes there. And above is just the formula for calculating the same thing. That means by symmetry under the normal curve, it's the same exact area that goes here. This is also 0.0325. It doesn't hurt to double check this. If you take 0.935, the center area, plus 0.0325, there's the 5, and then 2 copies of it, so go times 2. That should be exactly 1 for 100% of the area. And that's what we're getting in our calculator. So in my calculator that you're seeing here, this is input 1, the area. This would be input 2 and input 3, just 0 and 1. So at 93.5% confidence, we're expecting a number between these two values, 1.96, 1.645. So hit second vars. Really, it's like we're in chapter 5, section 4 once again. Go down to inverse norm. Area that I'm going to plug in, because this calculator only accepts left tail area, is 0.0325. And everyone's calculator could accept this. Just make sure you have left selected if it's a slightly more fancier version of the TID4. Mu we change to 0, sigma we change to 1. And that's what your calculator should look like. I went a little fast there. Let me go back. Your calculator should look like this before hitting enter. So if we hit enter on that, here's what we get. That's not what I was expecting. Hang on, let me clear this out. One more time. Second vars inverse norm. All right, I was expecting a negative number. Let's see what that comes out as. Yeah, that's what I was hoping to get. Negative 0.1845. Let's round this one to 3 decimal places, since that's what most of the table is doing. But notice the table's getting positive values. The reason I got the negative value is I used the left tail area. If I could use the right tail area, it would have came out as positive. So this one, as a negative value, is negative 1.845. But we have complete symmetry across this zero when we use the standard normal curve. It's negative 1.845. Over here, the actual value that we'd be giving is positive 1.845. And so that's the actual critical number that we'd be using. And yeah, it's between the 90% confidence value and the 95% confidence value. So for some people's calculators, you can either use central value, 0.935, right area, right tail value, 0.0325 would give you the positive. Everyone else's calculators like these give you the negative values. But you have to wonder, does negative matter? Because right there in the formula, you're using both positive and negative z star at the same time. Both of these values are going to be used. The positive value and the negative value both go right up in here. But if you're going to give an answer that says, what is the critical value? Most people would just report the positive value. So let's say here, the critical value is z star. We typically report the positive, 1.845. So now we can calculate confidence at any level of confidence. That's kind of cool in a way. And we can also double check one of these just as a really fast concept. But any questions at all, folks, coming up with the critical number z star?
The calculator doing the center thing gives you both positive, gives you both.
Oh, that's something I didn't know about that. That's kind of cool. It makes sense. Yeah, if there's a central value, it doesn't know which one's more important. So cool, it gives both. That's kind of a nice concept. One thing that's kind of tricky is if you're ever asked for a specific critical number and say MyLab statistics, again, it's only looking for the positive value. I wouldn't be picky though if you gave me both. Other questions so far? Okay, and just for the sake of showing how fast this formula is, let's double check a couple of these. 90% confidence came out as a pretty low value. That's interesting. The higher the level of confidence you are, the bigger the critical number. But that means the bigger this whole thing is, the more confident you want to be. So that's a concept to think about. But let's check out a couple of these values before we say more about that. Let's go to second vars. Back down to, let me put that back to the normal size, back down to inverse norm. And here's another really cool thing you could do in your calculator. You could just put in this whole formula just as you see it. You could go parenthesis 1 minus. Let's check out to 90% confidence. You would just take the 90% and write it in as a 0.90. 0.90 divide by 2. Keep these as zeros and ones. And that was not what I was expecting. Hang on, let me double check that. Second vars, I'm going to blame daylight savings on these weird issues. 1 minus 0.90, I did times 2, so that would be the mistake there. Go division by 2, that definitely makes a difference, right? And then enter on these. That's about what I was expecting. If you round this to 3 decimal places, it's negative 1.645. Convert to positive like we did on our problem below, and that's how we got that table value there. Back in the day before the TI-84 Plus calculator, people had to do this really, really meticulously. They had to go back to what we saw in 5.4, actually plot that function by hand and estimate these areas by hand. And they came up with really detailed tables of this kind of stuff. But that's the kind of work that takes years to complete. So it's kind of impressive how the calculator can just rip through these so fast. Any questions at all, folks, getting that critical number there? Okay, so this one's actually special. The 1.645 has been rounded to 3 decimal places. This one's been rounded to 3 decimal places as well. There'd just be a 0 in that spot, if I recall correctly. But that one's different at 95% confidence. Let's rerun it one more time to check out this value. Go second vars, inverse norm. I'm going to use a left tail area again, and through this formula, we're just changing this to a 0.95. So 1 minus 0.95 divide by 2, and this is what we get out for this one. Convert it to positive, so you get the positive result. But notice how accurate the table value actually is. If you round this to 4 decimal places, it rounds up due to that 6, and you get 1.9600. This one's actually more accurate than you might think. If you throw in the 00 for emphasis, it's accurate to 4 decimal places upon rounding. So that's a remarkably accurate value out of nowhere. And this one's not bad. It's just rounded to 3 places. And so is this one if you throw in the extra 0. Well, that's finding the critical number. Next thing we're going to do is just put it all together and write out some confidence intervals results. But one more related concept that we can talk about is this p hat is the point estimate for the unknown parameter p itself that we're trying to estimate. The margin of error is the z star times the standard error of p hat. So we can say margin of error is m equals z star times standard error of p hat. And here's what all of this implies. The larger the confidence, the larger the z star, the larger the margin of error. You cannot actually be 100% confident. That's impossible in statistics. Because if you get higher and higher confidence values here, the number z star over here, they just get larger and larger without bound. Let's see if we can push that. Let's go for 99.9% confidence, see what happens to z star. Hit second, vars, back down to inverse norm. Now let's suppose you want to be, get back to there, 99% confident. You would get that number, but what if you wanted to be 99.9% confident? You'd deal with this value in the calculator. Hit enter through this, and at 99.9% confidence, you're at 3.2. It jumped a lot. If you want to be 99.9999% confident and so on, these numbers just grow larger and larger. The moment you try to get to 100%, what happens is your entire confidence interval is now the entire real number line. And that gives you nothing valid as an estimate if you're talking about any range from positive into negative any longer. So there's kind of a limit here. Around here, beyond 99% or 99.9%, we usually kind of stop at that point because our interval is getting so wide, the margin of error is getting so huge that the interval you get is of little value any longer. So here's the bad part of statistics. No one is ever 100% confident, and you can't be extremely confident either, or else your interval is worthless. The sample size, however, comes into play as well. The larger your sample size, the smaller the standard error, but we're limited there. The square root is causing problems. You have to increase the sample size by a large factor to really make this small. And you can't make your sample size too large either. You're cost prohibitive, and you can't exceed 10% of the population size. So there's lots of limits to this, but at least we can put down an estimate. The big concept, however, is the higher the confidence, the larger the margin of error. That's the thing we're adding and subtracting, z star times the standard error. The larger the margin of error, And so this gives a wider confidence interval. So what we'll practice next is actually computing those intervals from start to finish. My first problem is not anything too major. It's kind of a refresher one, just so that we can focus on how the method works, how to use the confidence interval formula, and then we'll look into more trickier and trickier contexts as we go through the notes. But any last questions or comments at all, folks, with our brand new statistical inference procedure? Okay, let's work this out then on this next problem. Again, it's kind of a simple context. We've seen this context before. I've changed some of the numbers to a really large sample size, 1,024 patients. But the purpose of this example again is just so we can focus on the method itself before the context gets too hairy. So it says here, researchers in the development of new treatments for cancer patients often evaluate the effectiveness of new therapies by reporting the proportion of patients who survive for a specified period of time after completion of the treatment. It goes on to say, a new genetic treatment of 1,024 patients with a particular kind of cancer resulted in 173 patients surviving at least 5 years after treatment. So a couple things we can say right away is the sample size is the 1,024 patients and is 1,024. And this is all about surviving for 5 years after treatment. We had 173 in this study. It is fictitious data, but it looks about like what a real study could be. 173 patients surviving means there is 173 successes. So from there, we can now run through the entire procedure, culminating in part E, finding the confidence interval, and part F, giving the practical interpretation using the context. But notice there's kind of a lot of parts to all this. Condition checking is in the middle, but as an exam question, I probably would take this off because it's a pretty big problem as it is moving through these parts. I would make this a whole separate question on its own right. So first thing we want to do is describe the unknown, the thing we're estimating in the very first place, the thing that makes us do the whole confidence interval. We'll call that the unknown parameter. And for these data, if we say that there's 173 successes, that means the data is categorical. There's successes and failures. That's all we're doing is categorizing people according to those outcomes. And this means the parameter is P, the population's proportion of successes. And even though we're in context, and we definitely know in context of chapter 13, the only estimate is for P, this idea is kind of big because in chapter 14, there's different kinds of data. So just as a reminder, if the data is quantitative, then the parameter is mu instead, the population's mean. So here's how we tell what the unknown parameter is in the very first place, to determine if it's categorical versus quantitative. And chapter 14 is going to be looking into that quantitative data. So again, this is in context, but thinking of this as a problem on the final exam is definitely tricky because we don't know which chapter it came in from in the final exam problems. So we will always think in these kind of terms to start it off to determine what's the parameter in the first place. But now that we know it's P, let's just fill this in. P is going to be equal to the population proportion of, we say next what the successes were. The population proportion of was a success that is surviving at least 5 years after treatment. So let's say it this way, population proportion of patients surviving at least 5 years after treatment So this part right here is the successes. Next, we have to mention what is the population. So we'll say for all, and we could say, well, it can't be for all people, right? That's way too general. We have to narrow it down. Let's see here. This was for people who had a particular type of cancer, whatever cancer that might have been in this problem. And so that's what our population is. Not everybody, but anyone who had that one kind of cancer. So let's match the language and say, for all people with this type of cancer. And so when we said for all, this part right here is talking about the population. So it's pretty tricky stuff, but you can always go back to section 13.2 when we took a look into this before. Once that loads in, give you a moment. And 13.2, the little strategy we used was this structure right here. Hang on, I'm scrolling and not seeing, I think that was 13.1 rather. I'm already getting mixed up where things are in the notes. Let's try that one more time. 13.1, for how we did part A, you can use this structure that we laid down ahead of example 2. When we write down a parameter P, it's pretty much always this kind of thing. You don't have to say it in this specific order, but these are just the two elements we have to mention. We have to say what the successes were. You have to say what the population is. And we definitely have to mention, because the data is categorical, that the thing we're estimating in the very first place is a proportion. If the data was quantitative, we would have said the population's mean or average instead of proportion in this spot. What we got through, folks, that's writing down the parameter. This is really important because when we come back to part F, we need to say what the conclusion is in terms of that parameter we wrote down. So this is kind of doing half the conclusion already. The other half is just computing the confidence interval itself. Well, any questions so far before we try out part B? Okay, so this part is kind of the mathy portion. This is where it's not so bad. You just have to know what this means specifically. When it says sample proportion of successes, we're talking about p hat. P hat is the number of successes. Divide by the sample size. So that means in this problem, p hat is going to be the 173 successes that we identified, divide by the sample size of 1,024 patients. That number one looked a little odd. Let me fix that there. So there's p hat. We want it to 4 decimal places, so we'll throw it into the calculator and round. It comes out as 173 over 1,024 equal to 16.89. I said that weird. I guess I was thinking that as a percentage. As a proportion, it's 0.1689. Definitely write it down in that format. We don't want it as a percentage. It'll mess up the next formulas. But already we could say the thing that we did all the way back in section 1.1, P, the unknown, is approximately equal to the sample proportion of successes, the statistic P hat right here. But that's not the whole story. There's variability in our sampling. So that's why we're going forward for the standard error. We'll check a couple conditions and then look at the full 95% confidence interval. So that's just 1 point estimate. We want an entire interval estimate for the unknown parameter itself. Well, that's the standard error we're going to need next. Standard error depends on just what section you're in. If it's categorical data, if P came up here and P hat came up, the standard error is going to be described as SE for P hat, and it changes for quantitative data. This is the square root of P hat times 1 minus P hat, divide by sample size n again. So substituting in 3 different spots, P hat will go here, 0.1689. 1 minus P hat, so 1 minus 0.1689. Divide by sample size n, which is 1,024. So we just need to put this into the calculator, round this one to 4 decimal places, and we're nearly done with the confidence interval. So here's one way to do it. Hit second, power 2 to get your square root, and you could type in 0.1689. But if you are a fan of shortcuts in the calculator, here's another thing you could do. You can just up arrow, when it's highlighted, hit enter, and just directly copy it down. You're not using the approximated value any longer. You're using the whole accuracy right here. Even though it stops at 5, when you copy this down, the calculator is actually treating it as 173 over 124. So it's more accurate than you might even think. If you did this in MyLab statistics, you're still going to get full credit for that, even if you use the full value right here. And the reason to do this is it's fast. And if you're typing in a lot of digits, this is way more accurate. It just looks ugly in the calculator. That's a lot of stuff to stare at. Then match up the parenthesis, go parenthesis 1 minus. It's the P hat value again, so use the same trick. Up arrow, hit enter, and just throw it down in. You're just importing that value. Close the parenthesis, divide by 1024. And to 3 decimal places, this comes out as 4 places, 0.0117. Well, we got it, folks. That's the part C, calculating the standard error. Any questions at the moment getting through this one?
Did we go over how we would figure the standard error for quantitative data yet?
Not yet, but if you're curious, here's what it would look like. For quantitative, it's kind of a nicer formula. It's kind of strange. The standard error, we put in the statistic right here. So for categorical is P hat, but for quantitative, the statistic is the sample mean Y bar, and it goes like this. The sample standard deviation S divided by the square root of n. So it's kind of a nice formula. It's harder for categorical using this whole thing right here, which is kind of strange. Other questions at the moment? Okay, you might wonder, because this is actually kind of strange. Why are we doing categorical first if the formula seems just nicer for quantitative? And there's a really big reason for that. It turns out, as this reading might suggest, you're not using the normal distribution to get your critical numbers any longer when you're in this section. You're getting a different critical number, T star. This comes from something called the student's tables, or T distribution. If you go second vars, that's this one, inverse T. We're finally using other features of the calculator to get the different distribution. So something kind of strange happens when you're dealing with quantitative data, which is slightly more complicated than the categorical. So even though the formula is harder right here, the concept's a little bit more messy over here for what is T star in the very first place. But back to our 13.3. Next thing we're going to do is check the conditions. And that seems kind of tedious because we have checked conditions for this before, the different sample size. But for this kind of problem, the major conditions we're going to really look into are just these two right here. So that way we're not spending the full amount of time like we were in the prior section. If this comes in as an exam question and one whole problem is to check the conditions, I'll say what conditions we're checking. I'll say check the randomization condition, part A, check if the sample size meets the 10% condition, part B, and so on. So we know exactly what we're doing. But this one is just kind of a refresher. These are the two parts that we can directly check ourselves. These two major conditions. So let's check those two conditions, the ones we can actually see in the problem. Condition one is randomization. But the wording on this changed a little bit from when we looked at this very similar problem in the last section. Researchers in the development of new treatment of cancer patients evaluate effectiveness of new therapies by reporting proportions of patients who survived a specified period of time after completion of the treatment. A new treatment of 1,024 patients with a type of cancer resulted in 173 patients surviving 5 years. So after reading it again, nothing here said it was a random sample. So that means on condition one, the sample being a random sample, a simple random sample being the one we are most interested in, this is a total unknown. We'll say here, it is unknown if the sample is random. But now that we're looking at this, notice how slightly different these conditions are. This is what the actual condition checking might look more like in practice. The sample is a random sample. The golden standard for this is a simple random sample, like in the last section. But we don't always even have the simple random sample. Oftentimes in medical studies, even like these, sometimes they do studies on just the collection of patients that they happen to have. Then they might argue in some way that their patients are representative of the population of interest. That could require a lot of justification, a lot of argument. And this is something that makes some of these research journals really long. They have to actually justify, is our sample somehow representative, even if it wasn't random in the first place? That always gets really sketchy. It makes people really uncomfortable. So we hope that there's some randomization in the first place. This problem didn't mention it, so this is all we can really say. From the write-up of the problem, it being a random sample is completely unknown to us. But we can at least check condition two if the sample size is large enough for the central limit theorem to work. What we need is the number of successes in the sample and the number of failures in the sample to be at least 10. Sometimes we use this formula, and you could because you've got p hat right here. But other times the problem just tells you the number of successes, and that's the easiest way to do the problem in this case. So we can do condition two by saying the number of successes is 173, which is definitely greater than or equal to 10. So that was the benchmark we had to meet, larger than or equal to 10. And the number of failures is, we can take the sample size, n, minus the successes, 173, because there's only successes or failures. So the sample size was 1,024. We can read it from this number n going over to here for the 1,024, or scroll up just a little bit more. Minus 173. That's definitely bigger than or equal to 10, but let's just get a number just so that's not something that feels like it's hanging out there. 1,024 minus 173 came out as 851 failures. 851, there we go, which is also greater than or equal to 10. And that's what we wanted, at least 10 successes and 10 failures. So we can say here, the sample size is large enough. So the overall question two Are the conditions met or not? We don't know because we don't know if the sample is random. And so we can say overall, the conditions are met. If the sample is random. Or we could say the conditions are met if the sample was a simple random sample, or at least representative, but this is just a shorthand way of saying it. If it was random, it would have been representative itself. So that's a really abbreviated version of the condition checking. We checked 3 different parts, and we spent a lot more time on it in the last section. I felt like this was just kind of a reminder on the 2 critical parts that we could go over and determine exactly from what the problem tells us. From here, we can now do the confidence interval procedure itself by combining p-hat, the standard error, at whatever confidence level they decide to ask us for. Any questions at the moment? Okay, so let's do the 95% confidence interval part E. Well, first thing you'd want to do is, if it states 95% confidence, we have a critical number Z star we're going to be using. And one thing that's kind of funny about this class is people tend to memorize this one number pretty often. It's because 95% confidence kind of is a middle ground. Your interval isn't too wide at high confidence, it isn't too narrow at low confidence, which low confidence is not a great thing. But here's one thing you can do for this whole problem. Scroll up to where the confidence level table was given. You don't have to recompute these values unless I gave you a weird confidence. That's more MyLab statistics may do that in one problem, I would say. More often, you're going to just be using this table right here. And in a quiz on an exam, because these are more common values, I would be using these values here. So we grab the 1.96, 0, 0 if you like. I'll just do the 1.96 and import this value, 1.96. So the confidence level just immediately gives us the critical number Z star, which is kind of nice. But you know what's not so nice is if the data was quantitative, there was a mu in the problem when we calculate this different standard error. You have a T star instead of a Z star, and you have to calculate that one from scratch every single time. So inverse norm depends also on the sample size. So that's why this is a good problem to think about, because it's only in this section we have a table. For quantitative data, there is no nice table like this. We'll compute it from the scratch from the calculator, re-looking at that idea before. But now that we have the critical number, next thing to do is just write down the full formula. It goes p-hat, add or subtract the standard error, Z star, we already have that value, multiply it by the standard error of p-hat, we have that value as well. So now all we're doing at this stage is just making 3 big substitutions. So starting at the far left, the p-hat value is the 0.1689. 0.1689. Add or subtract 1.96, the Z star critical number, and then multiply that against whatever the standard error turned out to be. That was in part C, 0.0117. So that's our entire confidence interval. We have to crank it out. So now we go back to the calculator. But notice already from what we've done at the moment, we did something just like that. Right here in the notes. It was a very approximate 95% confidence interval. We put 2 right here because we hadn't had the concept of a critical number just yet. But we're not doing anything too different. We just happen to have a slightly more accurate value, a 1.96. We're going to put the unknown parameter p in the middle when we calculate the lower bound, and the upper bound just like before. So copying that idea, here's p. It goes in the middle. There's 2 sides to this. The left side, the lower value, is when we use the negative here. So let's carefully punch in 0.1689. Use the minus sign, 1.96. And either parenthesis or the multiplication symbol will work out just fine. 0.0117. Close the parenthesis, and this is our lower bound. It's 0.1460 a pound. Well, we're rounding to 3 places. That would be 0.146 to 3 different decimal places. So 0.146. Does that look okay to everyone at the moment? Okay, then we just put it back in the calculator again. But here's that trick that we've been talking about from way back in the day, like week 2 or 3. Hit up arrow twice, and you'll be way more accurate, a little bit speedy as well. The only thing we're changing is to a positive sign in the middle. So scroll over to that sign, throw in the positive, and that's the upper value. So essentially, if you put it in the calculator once, you've got it in there twice with that really fast trick. 0.192 rounding to 3 places. So that's our whole confidence interval. When you do this in MyLab statistics, they actually write it down as a mathematical interval. This is an interval 2 in inequality form. And so here's another way to present it. Let me write it this way, just as a reminder. This is how you'll see it in MyLab. The confidence interval is written more abstractly as an actual interval. It goes 0.146, comma, 0.192. So this is using interval notation from mathematics. It's the same idea, except we're vanishing p, putting a comma in place where the inequality signs were, and it has to go from lower to higher. If we mix up the order, they mark us wrong on that, which seems really, really awful. I wouldn't do that to you, but that's a MyLab thing. So make sure lower goes in first. Lower value here.
And a comma.
Yeah, I think often they'll print the comma for you. It's kind of like a little thing where there's just a placeholder for the first number, then the comma, and then another placeholder for the larger number. I would say not exactly. It'd be just basically reading it right to left if you flip the order. So MyLab would mark it wrong. They really want it left to right. But in other places, it wouldn't really mess up your interpretation because you're going to eventually say in part F, this is the last thing we'd be doing with it. The parameter P is between 0.146 and 0.192. If you said the parameter P is between 0.192 and 0.146, it's the same exact idea. It doesn't even sound that awkward, honestly. Other questions at the moment? Well, now the big question is, what did we calculate? That's a weird looking thing, right? It's an interval in inequality form here by the red dot, as an actual interval notation form over here in the MyLab statistics way. What we did over here, I wonder if we even wrote down an interpretation. We didn't. Well, we get to for the very first time then. So the major thing about statistics is this is useless to us. It's useless to everyone else in the public unless we can do our due diligence and say, what is that? What did we actually calculate? But this is the next cool thing. You go up to the top, and whatever you said in part A is the parameter P in the middle. So let's screenshot this temporarily. And this is what your conclusion would look like. Even if you made a mistake here, if you use what you said in part A, again, down here, you're not going to lose credit again. You'd be consistent and you get full credit for part F. It feels really redundant, so I have to be completely honest with you. Writing down the parameter once and again in part F feels very, very redundant, but I found over the years that if you do this as the very first thing in the problem, you're going to be way more successful in getting the practical interpretation in part F. Let's talk about this a little bit more. we're oddly specific with what we mean by a practical interpretation as well. A practical interpretation is meant to be an interpretation that someone will understand even if they have never taken a statistics course. So this was what makes it practical. In that sense, we don't want any specialized language. We have to say exactly what P is in the most reasonable kind of way. And so imagine kind of like you did an amazing study and now you're on Channel 8 News. You're trying to tell everybody what you found out. You're not trying to wow people with your specialized vocabulary. That's just going to confuse everyone and no one has any clue what you're talking about. You're trying to break this down for the layperson essentially. So that's what the practical interpretation is all about. That means you also have to use the context at the same exact time. But every single problem where this came up, where every time you looked at a graph or did anything at all and it said explain using the context, that's what this was all about, this particular problem right here. So it's as if we've been practicing, but you know what? If you said what the successes were and what the population was, you've already mentioned the context, so we've nailed that in part A. Finally, here's what the practical interpretation is going to look like. Now remember, the width of this interval depended on how confident you were going to be. It depended on that Z-star number. So the very first thing we do to be upfront with everybody is we tell them how confident we actually are. We start off by saying, with 95% confidence. And I regret that choice for color coding. I want to leave blue for the parameter P. So let me back off that statement. We're going to rewrite it with 95% confidence. Now we're just going to restate what we see in the interval. You have to expand out what P is using ordinary words. We can say the population. And it's your choice at this point. You could say proportion, or you could say percentage. If you go with percentage, this would be 14.6% up to 19.2%, or you could just keep it as a proportion, 0.146 to 0.192. I'll leave that completely up to you. At MyLab Statistics, it just depends on how they format the answer. Sometimes it's as a proportion, sometimes as a percentage. So we'll do it a couple ways in these notes. Let's stick with the proportion on this one just to see how it goes. The population proportion of patients surviving at least 5 years for all patients with this form of cancer Okay, so that's a lot of copying down, but it's verbatim, close to verbatim with what we wrote in part A. Looks like a change from this type of cancer to this form of cancer, but that would be okay if you change the language slightly. Now we just say is between 0.146 and 0.192. Or you could have said between 14.6% and 19.2%. If you decide to say percentage here. So that's finally the full practical interpretation. Just reuses whatever we said the parameter P was and says what values it's in between. We made it practical by not using a symbol like P or mu later on in chapter 14. And we mentioned the context several times when we talk about the successes and what the study was all about in the first place, the population. So that's quite a lot. There's a lot that goes into this. But you know this, that the meat about it is just calculate P hat, calculate the standard error, look up Z star. Now you have your interval, and just restate what the parameter was. You have to mention the level of confidence. You have to say what numbers it's in between. But after we practice this a couple more times, it's going to feel pretty routine. When we go to chapter 14, it'll feel like almost the same kind of stuff, except we're saying the population average or the population mean, and slightly different kind of methods. There'll just be a mu inside here instead of a P. Well, any last questions at all, folks? Getting to this last bit right here. Okay, at this point, it's good to talk about some interesting concepts. We've never said exactly what we mean by 95% confidence. So this is a good time to do that. So the problem has ended here, but there's so much to talk about with confidence intervals. Let's add some concepts below. So we must always mention the level of confidence. So that's just a reminder when we go to write out our practical interpretation. But now imagine this is a study with 1,024 patients. If you follow up on the study, you did a different simple random sample, you would have a different 1,024 patients. Your standard error is going to be slightly different, and your p-hat value is going to be different because the sample's different. They're all estimating the same thing, p, but it means that your confidence interval is going to have slightly different values for the upper value and slightly different values for the lower value and the upper value. I think I said that backwards at the start. But that's okay if our confidence intervals are slightly different. The remarkable thing about this percentage here, this confidence, is the following. If we repeat this study 100 times, this is assuming same population. We're not changing the population. We're not changing the notion of a success. Repeat the study 100 times, we get 100 different confidence intervals. And well, this confidence interval here, it could contain the parameter P, but that's not a guarantee. We're only 95% confidence it does. The parameter P could be larger than 0.192. It could be smaller than 0.146. And that's the same with all the other 100 different confidence intervals. The unknown is not guaranteed to be inside the interval, but here is the guarantee in this whole process. Repeat the study 100 times, get 100 different confidence intervals. 95% of them contain the unknown. I meant to switch colors here. Contain the unknown parameter P. And that's the big thing about what we mean by confidence. It's the success rate of the entire procedure. For the moment you identify the sample, chose a sample size, pulled in a simple random sample, we hope, and then constructed this interval, the success rate of the entire procedure, top to bottom, is 95%. We could have changed it to 99%, just change the z-star value, and our intervals are wider now. So this is a procedure that has a 95% chance of capturing the true and unknown parameter P in the middle, somewhere in the middle. So that's the major idea for what we mean by confidence in the first place. Any questions about that so far? So that's a pretty big idea. The next thing,
That's
yeah,
just
go
a
ahead.
Sidebar, right? Like, we don't have to write any of that stuff in the purple.
Yeah, that's correct. Yeah. So the whole problem really ends right below that vertical bar right here. That could be a really good thing to actually mention here. Let's call this additional remarks. Other questions at the moment? Okay, maybe another interesting question. Let's look at that interval again. This interval, for another additional remark, and there's so much you can say about these intervals, but another really important remark is this one. The exact center is not P. That parameter P is the unknown. And again, it could be closer to 1.46 or even less than. It could leave this whole interval. It could be in the center, but it also could be somewhere closer to 0.192 or even above 0.192. It could leave the interval on the upper end. But if it's not P, it is something else for sure. The exact center is P hat. That's because the method that calculates this interval went P hat, add or subtract a critical number Z star times the standard error of P hat. Because that's the formula that we use to construct the interval itself. We're adding and subtracting the same value to the P hat. That means the population proportion of successes P hat was the dead on center. And then the last concept here is the margin of error is half the width of this interval. So if you take this interval, calculate how long it is, divide it by 2, that is the margin of error. But we also know, because we've wrote it down several times, also it is m equals Z star times the standard error of P hat. It's still that same quantity. So the full width is when you added this value and subtracted this value. Half the width is just the margin of error, this thing itself. So we could calculate that ourselves. We're kind of shy on time. These are some interesting concepts to think about when it comes to confidence intervals. Like I mentioned, there's so much more. The reason we're talking about them is MyLab Statistics happens to have a way of putting in a concept question in some of the problems that you'll do. These are some of the concepts that can come up. And in the next problem, we'll look into some other ones. Like, for example, if you increase the sample size, does the interval become wider or narrower? If you change the confidence level, does it become wider or narrower? We'll look into some of those other concepts when we look into confidence intervals next time. But we'll look into another familiar problem next time, and then one brand new one to close out this section. Well, there's, again, tons of stuff to talk about because we're doing something pretty crazy. We're going all the way back to chapter 1. This was the biggest goal for the whole section, for the whole class. We're finally putting down this. We're describing exactly what is the accuracy and making this approximation. The interval is P hat, estimating P. But once you construct the margin of error, you're now saying what the actual accuracy is in making this approximation. We answer the whole question by constructing the confidence interval and saying it's 95% has a 95% success rate and actually capturing the unknown parameter P. Well, any last questions at all, folks, before we call tonight? Okay, lots of stuff to talk about with confidence intervals. That's just because we're seeing it for the very first time. When we're doing this in chapter 14, there'll be these same remarks, these same ideas coming back again, but just for quantitative data. So it'll be a lot easier when we see it a second time. But have a great night, folks. drive safe. It's a lot later out there than it really feels like. Thanks for daylight savings time ending. We'll be back to this on Wednesday.
Have a good night.
You too. Take care.